Alright, so this is going to be the Fast-exp problem, and we're going to be implementing the fast exponential problem that we might have done early in the semester in Python. And yeah, this is going to be on discussion number 11, and discussion number 11 on question number 10. And yeah, so let's dive into this. And so, if you remember from the time we did like fast exponential recursive in like Python, or like fast, just like fast exponential things, the idea here was that if it's even, we want to like take the value like b to the power of n divided by 2, and we're going to square that. So the idea here was that if we take b to the n power of n divided by 2, and we like square that entire thing, mathematics tells us that this is equivalent to b to the n. And so if you imagine, we're going to like go down all the way to the very bottom, and we're going to like square it back up. But the thing about like tail recursion is that, we can't make this work this way because like we have square. We're going to do something with the Fast-exp recursive after that. And so we can't do that because that's not tail recursive. We're only allowed to have this like fast recursive call. And so keeping that in mind, let's dive into like the fast exponential problem. And so let's start out with like maybe a helper function. So we're going to start out with b, n, and like our so far. And let's define this actually. So b, n, so far. And then what do we want to do here? Well, we want to have like the same logic as like this thing right here. Because the thing about like tail recursion is that the logic is going to be pretty similar, except for the fact that you like want to keep track of like your so far. And so let's copy paste all of that in. And let me fix like the tabbing a bit. Oh, shit. All right. And so we also have to edit like the base cases a bit, along with like tail recursive calls. And so if n is equal to 0, then we wanted to return 1 originally. But in the case of like our helper function, like since like in our recursive one, we took the 1 and then like we squared it all the way back up. Like we multiplied it by b, we like squared it, and etc. But in the case of a tail recursive call, we have that kept in the so far because like we can't square like after the recursive call. And so since we have it stored in so far, we're going to return that. So far. So we have our base case down, and we need to take a look at our like two situations, if it's even or if it's odd. And so one thing I forgot to mention is that at the very end, we're going to have a call to like our helper function. So it's probably going to be like helper something. But like, let's not look at that yet, and let's like focus on like the body of the helper. And so we are going to square like the Fast-exp recursive of b to like the n divided by 2. But in this case, since it's tail recursion, we have to do something different. And so we know that we have to start out with helper, because if we have anything before it, that's not going to be tail recursive, because like, if we have this of some like function applying it on helper, we're doing stuff with after, and that's like, we can't like close our recursive call for it. And so keeping that in mind, we have that if it's even, let me fix the parentheses. So it's even, then we have like helper of b and n divided by 2, like so far. We're going to do something with so far, but we have to figure out what we want to do. And so the question is, how exactly do we square it? Because originally we called square on the outside, but what about like the so far? So like if we might imagine, we're going to be multiplying so far by like whatever b to like the power of that is, because like so far is like keeping track of all the products. And so we might do like b times so far, but at the same time, how do we like address this? Because like we don't even know like how many times we want to like exponentiate b by like n divided by 2, so we can't just do something like b times so far, because like we have to multiply b by like a certain amount of times, more specifically b to the n divided by 2. We also can't do something like times like b to the power of n by n divided by 2. This is like kind of cheating, because like the power of b to the n divided by 2 is not going to be like the fast exponential stuff. And so we want it to be a fast exponential function. The question is, how do you do that? Well, one thing to note about like math in general is that if we have something like b to the n to the power of 2 and b to the power of n, it's equivalent to all right, sorry about that. But if we had something like b to the power of n, it's going to be equivalent to b to the b squared to the power of n divided by 2. Because the way exponentials work is that we're going to like multiply the 2 with like the n divided by 2, and that's going to be equivalent to like b to the 2 times n divided 2, which is equal to b to the n. And so keeping that in mind, let's think about how we can use this idea to put in our helper function. And so we have the idea of like b to the power of n divided by 2, and we can't really do anything with so far because we don't really know what to multiply it by. So what about putting square right here? And then, so the idea here is that when we see that it's even, we're actually not going to do anything with so far yet. But we know that we can like half things and like square the b. And so you might imagine, here maybe make some space down below, we have something like 3 to the power of 4. And this is going to become 9 to the power of 2. Actually, let me make this 6. And so this is going to become 9 to the power of 3. And then now we hit a case where it's odd. And then like so far might be like 1 right here. And so far it's still going to be 1 when we like do the helper. And then let's handle the case when it's odd now. And so in a like typical recursive function, we're just going to like multiply it by b. But we know that like from our experience with like Terra recursive functions, we can just like multiply by b right here. And so what's going to happen is that we're going to do like Fast-exp, and then we're going to multiply. We're going to do like b to the n minus 1, and we're going to store that information in so far. And the reason why we can multiply it by this compared to that is that we had to multiply this by like b to the n divided by 2, but that's like kind of hard to do compared to like making my bad, this should be the helper, making just the b times the so far. And so going back to like our example right here, what it might become, it's like 9 to the power of 2, and we're going to store the 9 that we took away inside the so far, and then this is even again, so it's going to be 81 to the power of 1, and so far it's still going to stay 9, and then we're going to go to, since it's odd, we're going to multiply it by 81, so it could become 81 to the power of 0, and so far it's going to be like 9 times 81, I think that's 729, and then because 81 to the power of 0, we hit our base case right here, and we're going to return so far, which is 729. And so that's kind of nice, because so the idea here is that like if it's even, we're kind of just going to half everything and like turn the 3 into like 3 squared and like half the exponent, because those are like equivalent. So like we're not doing anything, but we're like kind of changing like the base and the exponent. And then if it's odd, then we're going to like shift it down and we're going to multiply it by like whatever value that we have, because we're allowed to do that compared to when we had like the even part. Like you can't really like square so far because you're like squaring the wrong thing, and like you can't really multiply it by b to the power of n divided by 2 because like that's not allowed. And yeah, so we got that down, and now let's take a look at like our helper call, our main call. And so we want to pass in b and n because we're taking like b to the power of n. And what is so far? Well, because like everything is going to be multiplied. Oh, I kind of like gave it away in like right here. But we want to start out with 1, because if we have 1, then like if you think about like our factorial, for example, our base case was going to be 1 because we can multiply everything starting out from that. So like the same idea applies here. So we start out with 1, and then we can like multiply by 9, multiply by 81, etc. Like when you start out with like multiplication, you usually start out with the number 1. And yeah, that's going to be fast exponentiation, tail recursively. And yeah, if you ever have any questions about this, feel free to like email me.